Hello, welcome to the video presentation of my project that I did for linear and integer programming course. The topic that I chose for the project is to learn about non-linear programming and the methods that are out there to convert them into linear programs or linear constraints. Before we dive into the presentation, let me give you a brief introduction about myself. My name is Shreyas Kapoor and I am a first year Masters of Computer Science student at the University of Colorado Boulder. I started my master's in fall 2021 with the aim to gain knowledge in the data science field, and this course is extremely beneficial in helping me achieve that aim. So I took this course, and for the initial couple of weeks, I was confused as to how this course is going to be beneficial for me and my professional career. But during one of the lectures, the professor told us about how he and a couple of his students use linear programming to enhance a neural network. That got me thinking about ways to discover how linear programming can be used. While researching, I came across the fact that the world has more nonlinear programming problems than linear ones. Also, nonlinear programming problems are more difficult to solve. By doing this project, I plan to know about how linear programming is incorporated in real world applications and how the knowledge that I have gained during the course will help me in developing models in my career. The presentation contains a brief overview of what nonlinear programming is. Then, an example is shown to give an idea on how they are formulated. We then tell the issues NLP can run into, and finally, we talk about the solutions on how a nonlinear program can be converted into a linear program. Soon after the invention of simplex method, people began to realize the linear programming problem was too restrictive for most of the real-world problems that needed to be solved. Many problems have the extra constraint that some or all of the variables needed to be integer value. Thus was born the field of integer programming. Even more problems involve nonlinear functions in the objective function and or in the constraints, and so the subject of nonlinear programming also arose. A nonlinear program is an optimization program that can have a nonlinear or a linear objective function and linear or nonlinear constraints. If both the objective function and the constraints turn out to be linear, the problem is known as the linear program because linear programs are subset of nonlinear programs. The basic formulation looks like this. You have an objective function f of x which generally consists of nonlinear functions which can be contained in a column vector. The constraints are bounded by lower bound and upper bounds. The constraints can be of the equality nature like g of f equals to b or of inequality nature like g of x less than equal to b. Nonlinear program problems are iterative, which means that you have to take an initial guess and take the problem from there on. It can be any guess. The solvers gradually take the problem to the best solution following the gradient of the objective function and also following the constraints. This is assuming the problem is well posed and feasible. So for an example of nonlinear program, we have an objective function which contains variable in nonlinear fashion. We need to minimize 2x1 square minus 24x2 plus sine of x3 plus 300 such that x1 plus x2 plus x3 equal to 11 and all x1, x2, x3 are greater than 0. One of the issues to keep in mind during solving a nonlinear program is the non-convexity. At times, the problem may contain a local minima and a global minima. Suppose that we are to minimize f of x with x between 0 to 10. The point x equal to 7 is optimal. Note, however, that in the indicated dashed interval, the point x equal to 0 is the best feasible point. That is, it is an optimal feasible point in the local vicinity of x equal to 0, specified by the dashed interval. The example illustrates that a solution optimal in a local sense need not be optimal for the Overall problem. Two types of solution must be distinguished. A global optimum is a solution to the overall optimization problem. Its objective value is as good as any other point in the feasible region. A local optimum, on the other hand, is optimal only with respect to the feasible solutions close to that point. Points far removed from the local optimum play no role in its definition and may actually be preferred to the local optimum. Whenever the function curves upward, a local minimum will be global. These functions are called convex. Whenever a function curves downward, a local maximum will be the global maximum. These functions are called concave. For this reason, we usually wish to minimize convex function and maximize concave functions. There are quite a few solutions out there that convert a nonlinear program into a linear program and solve them. Let's go through them one by one. The first solution is RLT-based global optimization algorithm. But before we dive into the algorithm, let us explore what this new RLT term is. RLT, also known as reformulation and linearization technique, is developed by Sherali and Adams for 0-1 mixed integer linear programming problems. Constructs a hierarchy of polyhedral relaxations that spans the spectrum from the ordinary linear or continuous relaxation to the convex hull representation. Although the RLT was originally designed to employ factors involving 0-1 variables in order to generate 0-1 polynomial programming problems, they are subsequently relinearized. The approach can be extended in concept to continuous bounded variable polynomial programming problems as well. Problems of this type involve the optimization of a polynomial objective function subject to polynomial constraint in the set of continuous bounded variables. Note that the main function of RLT in the present context is to produce tight polyhedral outer approximations or linear programming relaxations for the underlying nonlinear, non-convex polynomial program. And as such, its principal purpose is to produce tight lower bounds on the problem. The key to obtaining global optimum solutions is to embed this RLT construct in a branch and bound framework, coordinating with it a suitable partitioning strategy that would enable the gap between the lower and upper bound, thus generated, to tend to zero in the limit. More specifically, this approach either solves the given polynomial program finitely, or else an infinite branch and bound enumeration tree is generated, such that along any infinite branch, any accumulation point of the sequence of solutions generated for the associated node relaxation solves the underlying polynomial program. In this algorithm, there are two methods in which, for the first one, we consider polynomial programming problems in which the variable have integral exponents for all nonlinear terms. The mathematical formulation of the problem is given. Problems of this type find a wide range of application in production planning, location, and distribution contexts, in risk management problems, and in various chemical process design and engineering design situations. To solve the objective nonlinear, non-polynomial program, the authors propose a branch and bound algorithm that utilizes specially constructed linear bounding problems using a reformulation linearization technique. In this approach, they generate nonlinear implied constraints by taking the product of bounding terms in omega up to a suitable order, and also possibly products of other defining constraints of the problem. The resulting problem is subsequently linearized by defining new variables, one for each nonlinear term appearing in the problem. The straightforward mechanics of RLT automatically creates outer linearizations that approximate the closure of the convex hull of the feasible region. In the RLT process, there are two steps. The first step is the reformulation phase, where we include the constraints shown in the original polynomial programming. The second step is the linearization phase, where in the reformulated objective function, we substitute the equation where the indices capital J are assumed to be sequenced in non-descending order, and where capital Xj is equivalent to small xj for all j belonging to capital N, and x phi equivalent to 1. This produces the required RLT linear programming relaxation. Before we further explore the algorithm, here is one lemma that we should know about. The lemma states that the value of the solution of linear program is less than the value of the solution of the polynomial program. Moreover, if the optimal solution obtained from the linear program satisfies the equation capital Xj equal to product of all small xj for all j belonging to this complex equation, then X star solves the polynomial program. The procedure involves the partitioning of the sets into sub-hyperrectangles, each of which is associated with a node of the branch and bound tree. Let omega dash be a subset of omega be any such partition. Then the linear program gives a lower bound on the polynomial program. In particular, if solution X solves the linear program, then by lemma, X bar solves the polynomial program. And being feasible to the polynomial program, the value V of PP is equivalent to V of LP, provides upper bound of the problem PP. Then we have a candidate for possibly updating the incumbent solution X star and its value V star for polynomial program. For step 0, initialize the incumbent solution and let incumbent objective value be infinity. Set X equal to 1, Qs equal to 1, and omega 1 equivalent to omega. Solve LP and let X be the solution obtained of first objective value. If X bar is feasible to the polynomial program, update X star and V star, and if lower bound equals V star, then stop. X star solves the polynomial program. Otherwise, determine a branching variable XP. For step 1, partition the selected active node into two sub-hyperrectangles by splitting the current bounding interval. Replace the two new node indices. For step 2, solve the RLT linear programming relaxation for each of the two new nodes generated. Update the incumbent solution, if possible, and determine the corresponding branching variable index for each node, as done for node 1 in initialization step. For step 3, fathom any non-improvement nodes. For step 4, select an active node and return to step 1. For branching, as indicated in step 1, we need to follow the given rule where X bar denotes the optimal solution obtained for the corresponding node subproblem. In the previous section, we considered polynomial programming problems in which the variables have integral exponents for all nonlinear terms. However, there are several applications in which polynomial programs arise, wherein the variable exponents are in general rational but not integral. Examples of such instances include water distribution network design problems, location allocation problems, heat exchanges, and pressure vessel design applications. Similar to the previous section, a branch and bound algorithm is developed that solves the sequence of relaxations over partition subsets to find a global optimum solution. However, to generate the relaxation for each node subproblem, an additional initial step is introduced that constructs an approximating polynomial program having integral exponents on which RLT is applied. Furthermore, to ensure convergence to a global optimum, special partitioning procedures are proposed to coordinate the two levels of relaxation that are involved in this scheme. This gives the basic structure for the algorithm, to which several expedients and reductions or bound tightening strategies can be applied. There are two steps in the reformulation phase of this algorithm. In step 1, given a polynomial program, generate relaxed polynomial program given by the equation shown. Let delta denotes the degree of the relaxed polynomial program. For step 2, let n bar denote replication of n. Compose all distinct possible constraints obtained by taking product of bound factors, and then augment the relaxed polynomial program by adding these constraints. In the linearization phase, linearize the resulting polynomial program obtained at the end of the reformulation phase by the given equation, and then denote the linear program thus produced by LP of omega. With the exception of the partitioning rule, the proposed branch and bound algorithm proceeds precisely as described in the previous section, which is by using the linear program obtained by the above RLT process to generate a lower bound for any node subproblem defined in the subset hyperrectangle of the original hyperrectangle. The critical element of difference that guarantees convergence is a global minima for this rational exponent case. Is the choice of the suitable partitioning strategy. There are three such branching rules that can be used at reformulation phase in order to assure convergence to the optimum. The first of these, rule A, is a simple standard bisection rule. While this is sufficient to ensure convergence since it drives all the intervals to zero for the variables that are associated with the term that yields the greatest discrepancy in the employed approximation along any infinite branch of the branch and bound tree, it is not too cognizant of the nature and solution of the employed relaxations. The rule B accordingly suggests branching at the value x itj. Whenever the approximating problem employs the tangential approximation at this point for the term under consideration, motivated in part by the fact that the tangential approximation is exact at this point. Likewise, Rule C is further oriented toward computational effectiveness of combining Rule B with a partitioning at the linear programming relaxation value whenever admissible. Since the RLT approximation involving any variable becomes exact whenever this variable coincides with one of its bounds. Hence, by letting the current linear programming relaxation value become an upper interval bound on one partition subnode and a lower interval bound on the other, we encourage the tightening of the resulting relaxations. In the mid-1980s, N. Karmakar invented a new algorithm for linear programming known as the interior point method. He proved that this algorithm has polynomial time worst case complexity, something that has not been yet established for any variant of the simplex method. Furthermore, he claimed that the algorithm would also be very good in its average case performance. So, the question arises, do interior point methods have a natural extension to nonlinear programming? And if so, how do they compare to the natural extension of the simplex method to such problem? The answer is yes. There is a very natural extension, and yes, the methods perform very well in this context. In fact, interior point methods are best understood as methods for constrained convex nonlinear optimization. Robert Van der Beek developed a software known as Loco, which implements an interior point algorithm for nonlinear programming. The basic family of problems that the software solves are given as minimize f of x subject to some function h of x bounded by b and b plus r, and x bounded by some lower bound and upper bound. The software assumes that the function f of x and hx must be twice differentiable, but not necessarily convex or concave. The standard interior point algorithm can be described as step 1, add slack variables as to replace all the inequalities and non-negativities. Step 2, replace non-negativities with logarithmic barrier terms in the objective that is in the form mu of log x, where mu is a positive barrier parameter and s is a slack variable. Step 3, write first order optimality conditions for the barrier problem. Step 4, rewrite the optimality condition in primal dual symmetric form. This is the only step that requires linear programming for its intuition. Step 5, use Newton's method to derive search directions. The resulting linear system of equation is shown. Here, matrices D and D are diagonal matrices involving slack variables. Step 6, compute the step length that ensures positivity of slack variables. Step 7, shorten the steps further to ensure a reduction in either infeasibility or in the barrier function. Step 8. Step to the new point and repeat. Another solution is separable programming, which solves the optimization problems of the form shown, where the function fi and gij are known. These problems are called separable because the decision variables appear separately. One is each function g of ij in the constraints and one is each function f of j in the objective function. Separable programs arise frequently in practice, particularly from time-dependent optimization. The model also arises when optimizing over distinct geographical regions, an example being the water resource planning. Consider the example of maximize fx is equal to 20x1 plus 16x2 minus 2x1 square minus x2 plus x1 plus x2 whole square, subjects to x1 plus x2 less than equal to 5 and x1 x2 all greater than equal to 0. This problem is not separable because of the term x1 plus x2 whole square in the objective function. Letting x3 equals to x1 plus x2 through, though, we can re-express it in a separable form. Thus, it is clear separable. Clearly, the linear constraints are also separable. Algebraic procedures such as pivoting are so powerful for manipulating linear equalities and inequalities that many nonlinear programming algorithms replace the given problem by an approximating linear program. By using different approximation schemes, this strategy can be implemented in several ways. One such way is Frank-Wolf algorithm. Let X not be any feasible solution to a nonlinear program with linear constraints. Here, X naught might be determined by phase 1 of the simplex method. This algorithm forms a linear approximation at the point X naught by replacing the objective function with its current value plus the linear correction term. This, where Cj is the slope or the partial derivative of f with respect to xj, evaluated at the point xj. Since f of f naught cj and x naught j are fixed, maximizing this objective function is equivalent to maximizing the function this. The linear approximation problem is solved, giving an optimal solution y. At this point, the algorithm recognizes that although the linear approximation problem indicates that the objective improves steadily from x0 to y, the nonlinear objective might not continue to improve from x0 to y. Therefore, the algorithm uses a procedure to determine the maximum value of f of x along the line segment joining x0 to y. Some more methods that are out there are as follows. The first being map, or method of approximation programming. The Frank-Wolf algorithm can be extended to general nonlinear programming by making linear approximation to the constraints as well as the objective function. The method of approximation programming is a simple modification to the previous approach to limit the size of the move. As a result, it is sometimes referred to as a small step procedure. Generalized programming is applied to the optimization program of selecting decision variables from a region. The procedure uses inner linearization and extends the decomposition and column generation algorithm. When the objective function and constraints are linear and the region consists of the feasible point for a linear programming subproblem, generalized programming reduces to the decomposition method. Quadratic programming concerns the maximization of the quadratic function subject to linear constraints. As we come to the end of our presentation, I would like to thank the authors of these books, which were extremely helpful to me in completing my research into the topic. Thank you for watching this presentation.